welcome back. And today we're going to be talking about a little bit more of a complicated topic in ecosystems. We're going to be talking about energy flow and carrying capacity. So since it's a little bit more challenging, I chose to do a video instead to walk you through this. So we're going to start by talking about the concept of energy flow, and then we'll move into ecosystems. So I just want to remind you kind of where we left off last time. And where we left off was this idea of the trophic level. So this entire thing here can be called an energy pyramid. And if you look at the very base of the energy pyramid, we have the producers. Then we have our primary consumers, secondary consumers, and tertiary consumers. So if we were going to link this to our food chain activity that we just looked at, your producers would have been your grass on the bottom. Then you had your rabbits, were primary consumers. They were consumers because they ate grass. Then you had your secondary consumers. That would have been your snakes. Your snakes fed on your rabbits. And then your tertiary consumer would have been your hawk, which is at the very top there. So producers are essentially always plants. They're called producers because they're able to produce their own energy from the sun. Then any of these consumers have to feed on your producers down here. So I'm going to be coming back to this food pyramid in a second. First of all, I want to talk about these laws of thermodynamics. So part of this is the reason that I chose to make this video. A lot of students will see the word thermodynamics and freak out a little bit. Thermodynamics are really important in chemistry, and they're very important in physics, but they have a role in ecology as well. They sound confusing, but they're really not. So first of all, we are going to start, and I want you to take your hands and rub them together. So you can hear me doing this on this end as well too. You're going to then put them on your face. And I want you to think about what happens. What you should have noticed is that your hands become hot, and then that heat, that energy, you can actually feel it on your face when you put your hands there. That's the transfer of energy, and that has to do with our thermodynamics. So what our first law of thermodynamics, our first law is going to state is that energy cannot be created or destroyed. It just changes forms. So when you were actually rubbing your hands together, putting that energy in, you were taking kinetic energy, movement, and you were changing it to thermal energy, heat. That energy could then be transferred to your face. So that energy wasn't destroyed at all. It just changed from kinetic energy to thermal energy, and then we could feel that on our face. So what does the first law of thermodynamics have to do with ecosystems? This has to do with all living things. So this means, we're going to read this first sentence here. This means that all living things must have a source of energy. So the fact that energy cannot be created or destroyed, but we need energy to live, that means that our energy must be coming from somewhere else. We can't create our own energy, so we have to get our energy from somewhere else. So the energy that I get, that I need in a day, is going to come from my food. Where does my food get its energy from? That traces back to that energy pyramid, and ultimately, this second point here, our ultimate source of energy is from the sun. So sun gives energy to plants, and then you might eat a plant, or you might eat something that eats a plant, or you might eat something that eats something that eats a plant. But essentially, everything is going to trace back to these producers here. And right below these producers would be the sun. The sun creates energy. How? We'll talk about that a little bit more in Unit 4. That energy gets transferred to producers, who transfer their energy to primary consumers, secondary consumers. So essentially, we're going to see a flow of energy up this food pyramid, transferring the energy up each step that you go. That's going to bring us to the second law of thermodynamics. And the second law of thermodynamics, let's read this together. The second law of thermodynamics states that at every single energy transfer, some of that energy is lost to heat moving to cooler objects. So that means that each step that you take up that energy pyramid, when you go from producers to primary consumers, or from primary consumers to secondary consumers, you're losing some of that energy from heat loss. So whatever food that I eat, I'm losing some of that energy to heat loss. Let's talk more specifically how much energy you're losing. Energy is lost each time an organism eats another. Each level gets about 10% from the trophic level below. So if we were going to restate that, 90% of the energy is used by the organism to stay alive. So 90% of the energy within an organism is going to be used to stay alive itself. 10% is going to be transferred to the energy level above. So let's talk about this in our food chain again. And we're actually going to see why our populations look the way that they did in our last exercise. So here we have our grass was at the very bottom of our energy pyramid that we did last time. So our grass was at the bottom. Those were our producers. On top of that, there were rabbits. So you would have noticed that in your stable population, you had far fewer rabbits than you did grass blades. This is because every time that a rabbit eats grass, there's energy being lost to heat loss. So a rabbit isn't happy just eating one grass blade. That's not going to keep its full. A rabbit has to eat lots of grass blades in order to get enough energy to sustain itself. Same idea with the snakes. So the snakes were above the rabbits. You would have seen the population of snakes was a lot smaller than that of rabbits because a snake needs to eat more rabbits than one to stay alive. And same idea with the hawks. So if we go back to an energy pyramid, if you notice this tertiary consumer line is much smaller than the one below it, that's what gives it the pyramid shape. This is on purpose. This actually represents a population size. So to have a stable energy pyramid, you have to have your smallest population at the top and you have to have your biggest population at the bottom for it to be stable. If the bottom is too small, there's not enough energy flowing upward and your ecosystem will collapse. So I would just want to draw attention to some of your these numbers here because this is going to come back if you take senior physics. So you're going to see producers have something called 10,000 kilocalories of energy. You might have heard of the word calorie before. Calorie is just a unit of measurement of energy in physics. So when I say I'm eating 2,000 calories a day, that means I'm eating 2,000 units of energy. So if the producers have 10,000 kilocalories, only 1,000 kilocalories will get transferred to the consumers, 10%. Only 10% will get transferred to the snakes, and only 10 kilocalories will get transferred to this eagle. So there's very little amounts of energy available at the top, which means that there's very few eagles at the top of this energy pyramid. So to summarize, the movement of energy through an ecosystem can be summarized by an energy pyramid. Since we lose energy at each trophic level, each step up the pyramid is going to get smaller, and energy can be measured in something called joules. We saw that unit in physics, or kilojoules. There's 1,000 joules in a kilojoule. We're going to look at two trends in energy flow now. So our trend in energy flow has to do with the size of our pyramid. So we mentioned this before, but this is a nice diagram to show us. It says that because energy is lost at each step, this sets a limit on the number of trophic levels to about 5. So in any ecosystem, you won't typically see more than 5 trophic levels. The one that we looked at last time actually only had 4. So the trophic levels are producer, primary consumer, secondary consumer, tertiary consumer, and the last trophic level that you might see. So if there was something feeding on the hawks, we would call that the quaternary consumer. So that fifth trophic level can exist, but we don't typically see it. So what controls an ecosystem? What's more important? Scientists actually have 2 different theories around this. The first theory that we call is called the bottom-up control. So what we mean by control is essentially what's more important. And you tried to answer this in the last activity. Is it predators that are more important, or is it prey that are more important? In bottom-up control, this hypothesis states that producers, the bottom of the pyramid, is actually what's going to control the ecosystem. So the number of trees or the number of grass blades is going to determine how big this ecosystem can be. And at first glance, this is totally correct. But now let's take a look at top-down control. Top-down control theorizes that predation at the top is actually going to control the ecosystem function. So if we have a lot of lions, that's actually going to limit the number of giraffes. By limiting the number of giraffes, you're going to be able to have more trees. So when you think about it, it's actually probably a combination of both top-down and bottom-up control. The number of trees is very, very, very important in an ecosystem. It determines the number of giraffes, which is going to support the number of lions. But this top-down control is also important. The number of lions at the top here is going to keep the giraffe population in check, which is going to allow the trees to grow. So the predators at the top are also very important in an ecosystem. We want to make sure that they're present as well too. All right, so that's our first idea of energy trends. This is going to lead us into the second part of your activity that we looked at, and that has to do with populations over a long period of time. So we're going to look at different factors that are going to affect populations. So there's lots of factors. You looked at predators, you looked at prey, but there's a lot of ideas coming into play here. So first of all, let's look at what a population is. A population is a various combination of abiotic and biotic factors that can cause populations to change. So let's take a look at some of these factors. These are all things that might cause a population to increase or to decrease. So let's look at something that might cause a population to increase, something that might cause a population to grow. Those of you that have had geography, you might have seen these terms before. So natality means birth rate. So the number of species that are born is going to cause a population to grow. If you have a very high birth rate in a population, you're going to see a bigger population. If you have a low birth rate in a population, you're going to have a lower population. The other thing that can cause a population to grow is this concept of immigration. Immigration is moving into an area. So I always see this I in front of immigration and think about species moving in to that area. This here on this side is all factors that can cause a population to decrease. The first thing is mortality, that's death rate. So if you have a really high death rate, that's going to decrease your population. If you have a lower death rate, that's still going to decrease your population, but at a lower rate. You also have this concept of emigration. Emigration, a lot of students get confused with emigration and immigration because they sound similar. So emigration, I look at this E in front and that means exiting. So emigration means exiting or moving out of an area. So overall, our population growth is going to be a balance of factors that add to and take away from our population. So we tend to have this kind of magic formula that ecologists will look at, and they'll look at the factors that add to a population, that's births and immigration, and they'll subtract the factors that take away from a population. This is deaths and emigration. So if the number of things that add to a population, births and immigration, is higher than the number of things that takes away from a population, deaths and emigration, you're going to see positive population growth. But if the number of things that take away from a population is larger, so deaths and emigration, you're going to see population growth decrease or a negative number. So birth rate and death rate actually tend to have the largest impact on population size. So species moving into an area or out of an area don't have a larger impact. More so, it's the birth rate and the death rate that's going to see the largest impact overall. A couple different terms that we want to look at. The first term is this idea of an open population. So an open population is going to allow for births, deaths, immigration, and emigration. So essentially, open means that there's no barriers. So something like a forest, a lake, or a field isn't going to have any barriers on population. Whereas a closed population, it's not allowing individuals to move into or out of an area. So you've essentially taken away immigration and emigration. So a great example of really small but really good examples of closed populations might be a fenced yard. A fenced yard means that things can't move in or out, game reserves that are protected, or even a laboratory setting. We're going to skip over this one for now. We're actually even going to delete this because we don't need to talk about that. What we want to focus on is we want to focus on the idea of limiting factors. So limiting factors are what's going to prevent this idea of overpopulation. So you might have seen this in your activity. If you have too big of a population at the top, you're not going to have enough resources to survive. So if you have too many hawks at the top, there's not going to be enough snakes to keep the hawks alive. So overpopulation isn't good. We're going to run out of resources. So limiting factors help to prevent overpopulation. It's a factor that's going to restrict populations. So let's first look at abiotic limiting factors. Remember from last week, abiotic means not living. So abiotic is anything that's not living in the population itself, but might limit factors. One thing might be the amount of light. If you don't have a lot of light in a population, you're going to limit the number of plant growth. If you're limiting the producers, you're limiting the population overall. Temperature, if it's too hot or too cold, you might limit plant growth or the species that survive there. Acidity. So we talked about acidity a little bit in chemistry. Acidity has to do with the pH. So if you have too acidic of an environment in a lake or a pond, a lot of species of fish and a lot of species of plant can't survive in acidic populations. A natural disturbance like a drought or a volcano might wipe out some populations, or the most important, and we're going to focus on that next week, is going to be human disturbances. You also have biotic limiting factors. These are things that are living that might also limit population. So things like competition. So two living species are going to vie for the same resource. This is going to limit one of the species' populations. We're going to talk about this a little bit more next week. Predation, that's one species feeds on another. Again, we're going to talk about this next week. And symbiosis, that's two species that live near each other. This might be good, this might be bad, but again, we're going to talk about that next week. All of these factors are going to come together in this idea of carrying capacity. So carrying capacity is, again, another term that you might have seen in geography. In carrying capacity, it's essentially how big a species can get. So let's look at this first point together. As the population grows, it requires more food, water, and space. At some point, the population reaches a maximum number of organisms that it can continuously support. That essentially is carrying capacity. So the largest number of species that a population is able to support based on its resources. So carrying capacity, by definition, the maximum population size of a species an ecosystem can sustain. And ecologists will actually use a graph and a mathematical formula to actually be able to figure out what carrying capacity is. So we're going to be looking at graphs. We're going to look at a simple one on this slide and a more complicated one on the next slide. So let's talk about, in theory, the number of rabbits. So we're going to have the number of rabbits, the population size of rabbits on this side of the graph, and let's have the time passing at the bottom of the graph. Let's say that this is in months. So at first, the population of the rabbits is going to grow very slowly. And then all of a sudden, the population of the rabbits is going to grow quicker. And then at some point, the population of the rabbits is going to slow down. You would have seen a slowing down in your graphs or a steadying of your graphs in the last activity that you did. This straight line here, this steadying, is actually called the carrying capacity. So at this point, this is the carrying capacity of the rabbits. The ecosystem can no longer support more rabbits. This might be due to lots of factors. Maybe we've run out of grass. Maybe we have a set number of predators. Maybe we've run out of mates and the rabbits can't reproduce. So there's lots of things that can set carrying capacity. All of these factors that we looked at, abiotic and biotic limiting factors, are actually what's going to determine the carrying capacity of a species. Now let's look in a little bit more depth at a population growth curve and what's happening in each of the areas. So we're going to find our first area here is going to be at the very start. We saw a slow growth, a slow population of rabbits. That's because there's still a small number of organisms and they're adjusting to their new environment. So they're trying to figure out what the food sources are. They're trying to figure out how to survive against the predators, and there's a smaller number of species in order to mate. So you're going to see not necessarily a doubling or tripling of population yet. Then all of a sudden, you see this area of rapid growth. This is because the organisms are now ready to reproduce. So they've acclimated to their environment and they're now able to reproduce at a steady rate. So we're going to see exponential growth. We're going to see a very quick, rapid growth. Then we get to our last region here. This is the region of steady population growth. This is carrying capacity. So what this looks like is a flat line. In all reality, it's not necessarily a flat line. It actually fluctuates. So population might go up a little bit, then all of a sudden we run out of resources. And then population might go up a little bit again, and then there's a natural disturbance, and then population goes up again, and then all of a sudden maybe there's a predator that comes in. So it's going to be more of a jagged line, but it's going to stay around the same number. So this is carrying capacity. Sometimes ecologists will use the letter K to represent carrying capacity. So this K that's here is the exact same as the word carrying capacity that was on our last slide there. So carrying capacity can be altered through natural or human activity. So these are just a couple examples that you might see of carrying capacity being altered. So a forest fire can actually increase the number of blueberry bushes since more light or space is available. So this carrying capacity, this number isn't necessarily set. Sometimes you might see a higher carrying capacity or a lower carrying capacity. Another example, irrigation. So that's the increase of water flow, which increases the productivity and fertility of a land, can change a desert into a lush oasis. So humans can come in, help to water plants in the desert, and that can cause more plants to grow and a higher carrying capacity. Or more commonly, you might see the removal of wolves by hunters. This can cause an increase in deer population since there are fewer predators. So next week, we're going to be studying how humans might have different interactions and how we might disturb the natural carrying capacities that exist in the environment. So at the end of the day, for an ecosystem to be sustainable, none of the populations can exceed the carrying capacity for very long. So the idea of carrying capacity is actually to keep populations in check. If your carrying capacity is exceeded for too long, you will eventually run out of resources. All right, thank you so much for sticking with us, and join us next week, and we're going to take a look at some of those human disturbances. Have a great week, and we'll see you again soon.